Okay, this is going to be the video for 15.1 and 2, which is the introduction to the idea of multiple integrals. We're going to be focusing in Chapter 5 on how to do integration with multivariable functions. So we have one output variable, but one output of the function, but it's based on more than one input. And we'll first talk about double integrals in 2 dimensions. The domain is 2-dimensional, and then we'll talk about multiple integrals in 3-dimension with a 3-dimensional domain, which is called triple integrals. And we're going to split the chapter into 2 halves: double integrals, triple integrals, and we'll have separate tests over each of those. And then after that, there's only one more unit, but these last, or one more chapter. But these last 2 chapters are very involved, and there's a lot going on, so they're going to take the entire rest of the semester. In fact, the chapter 16, typically we don't finish it in first semester, and we have to let 2 sections get taught in the next in third quarter, which we'll talk about that as we get to the end of the class. So point is, this stuff is pretty involved, right? So if it feels a little overwhelming at the beginning, that's fine. Just stick with it, right? And you'll eventually get there, right? So as long as you're staying, it's especially important to do all the homework every day in these sections. All right, so let's take a look at the notes for section 15.1 and 2. 1 is very short. 2 is where most of the work is, and homework for this will be in section 15.1 and 15.2 both. All right, so let's talk about what is a multiple integral. Let's see, I don't really see my presentation coming up here. Let me make sure that that is coming up. I want to present this window. Oh, there it goes. Okay. All right, so we're going to talk about double integrals, and first we're going to talk about integrating over just a rectangular region in the domain, and we'll talk about something called Fubini's theorem and how we can evaluate definite integrals using the integrated integral method. So first, let's talk about what is even a multiple integral. So in single variable calculus, we know that the integral is the area under the curve, among other interpretations, and it can be related to something called a Riemann sum. So we first learned about the idea of an integral, and in my mind, an integral is an object, a mathematical object, which sums up things, right? It basically allows you to smoothly sum an infinite number of things, right? The first thing that we had integral sum was rectangles to find areas under a function curve. So if we had a function curve like this, and we wanted to find the areas from some starting x to ending x or something like that, then we could divide that into different shapes here that then we would add up. And when we do that, it's called computing a Riemann sum. And in Calc 1, we even introduced this back in brief calc, but in Calc 1, Calc 2, they usually talk about different sorts of things, like sometimes they divide this into rectangles, sometimes it's rectangles where the height is established by the middle value, which is called the midpoint rule. Sometimes they use the left endpoint or the right endpoint. Sometimes they use trapezoids to get better things, Simpsons. There's different kinds of shapes that you can use to do this numerical estimation of your area under the curve. But the simplest one, and the one that I just remember conceptually, is if you divide up the domain into some even intervals like this, and then you just use each of those intervals, pick a value like in the midpoint to establish the height, then you can get a width times a height to find an area, a 2D area, and then you can just sum up all those areas to find the approximate area under the curve, right? The area is a sum of heights times widths. The widths are little changes in the domain x direction, and the heights are given by a function value for an x at that position along the domain. Right, and then what we would do to try to make this very close to the area would be to take the limit as the number of rectangles approaches infinity, or as the width goes to 0. And when you do that, then this summation becomes a smooth summation, which is an integral, right? Integral from a to b of some function value times dx, and the delta x becomes the differential dx. But what we're doing is finding a whole bunch of little areas of rectangles summed up, right? All right, so if we had a multivariable function where we had z is a function of, we'll consider first 2D, z is a function of x and y, then that means that the domain is 2-dimensional, right? So we have a 2-dimensional domain down here. right? And the output z is in this dimension, and so the surface here represents all the output values across different places in the xy domain, okay? And so we could do something that's like an integral, except instead of summing over just one direction for the input, we would have to sum over x and y. So now we could take like a little change, whereas before the change was just a length, right, delta x. Now the change is going to be a little area. It's going to be a change in the x direction, delta x, but also a change in the y direction, delta y. So it gives me a little delta area, right? I've got a little tiny delta area there in the domain, right? And then if you pick a representative xy value in there and you plug it into the function, you'll get a height, right? So this is f at xy, right? And so if you multiply the height times the area, then you're getting a volume. So now when we do what's called a double integral, we're finding the volume underneath a surface over some particular region in the domain, right? So it would be a double integral. You would have to take the heights times the areas. This is delta x times delta y in this case, right? And then you would sum them up over one of the things, like sum them up in this way, and then also sum them in this direction, right? So that you're summing over both, right? And if we use a smooth version of that with an infinite number of little tiny delta a's, then the delta a becomes the differential delta dA, an infinitesimally small area in the domain, over some region r in the domain. So this is the region r in the domain. And then times the fxy gives you the height, so you have heights times area, a little change in area to give you volumes, right? So this is the 2D equivalent for a multivariable function of an integral. And this is called a double integral over region R. Okay, so we could approximate that by adding up little rectangles, just like we did for like a 2D version of a Riemann sum. And we could use the midpoint rule, where we're going to use the middle of this little change in area here to establish the height. So let's say that we wanted to evaluate this function, right? The volume underneath this surface, z equals 16 minus x squared minus 2y squared, just in the region that's covered by x equals from 0 to 2 and y goes from 0 to 2, right? So this is the region in the domain that we're covering, R. And we really want this total volume underneath the surface, right? So let's just divide it into 4 equal regions with 1 on each side. And then we'll go to the midpoint to establish the height. So for example, I could pick a point for this first region here. Let me highlight it in red. Okay, so here's this first region in the domain. Here it is down here in the domain. Okay, and the point that I'm going to use to the xy that I'm going to use to establish the height is going to be the point 0.5x, 0.5y. Right, so I'd pick an arbitrary point there. We're just going to use the middle, okay? And then I would plug that into the function to establish the height, right? So this height here would be, if you trust me, plugging this into this function would give you 15.25. You can do that yourself if you like, right? And then I'm going to take that area, or that height of 15.25, and multiply it by the area, which is 1 by 1. So this is a little area of 1. And so if I take 15.25 height times an area of 1, then I get 15.25 cubic units of volume. That's the volume contained in this little rectangular region here. So in this little rectangular region, there's a sliver of volume. You could do that for each of these. So we could go over to this point here, which is 0.5 in the x and 1.5 in the y, the middle of this little square. If you plug that into the function, you would get 11 times an area of 1 gives you a volume of 11. Then if you did this point here, which is 1.5 in the x direction, 0.5 in the y, you'd get 14 when you plug that xy in for the height times 1 would give you 14. And then if you go to this last point, which has an x of 1.5 and a y of 1.5, when you plug 1.5, 1.5 in here, you get a height of 10. And so 10 times 1 is just 10. And then you could add up all those volumes to get 50.25 cubic units, right? and that would be the volume. That's an approximation for the volume. And of course, it's not completely hitting it, right? Because we have some area that's not getting covered and some area where this is sticking out. So there's some overage here. There's some underage, it's over and under. So maybe that'll balance out if we use the middle points. But of course, we would really want to be able to do this with integrals and like the fundamental theorem of calculus to not have to live with an approximation. Okay. All right. So there's various things you can do with these. For some reason, they decided to put in 15.1 and 15.2 average value. This is just one of many, many uses of multiple integrals. So I'll just talk about that now. We know that if you're averaging something, right, what you're essentially doing is adding up the totals divided by the number of elements. If you have discrete numbers, then you literally add up the numbers and divide by the number of elements, right, the number of numbers. But in single variable calculus, we learned that the way you add up things is with the integral, and then you divide by the width of the interval, right? And that gives you what's the average value, right? It's the value. So what we're really doing here is saying we have a function value from a to b, f of x, and we want to know what's the average y, right? So you add up all the y's using an integral from whatever the y's are here to here, all these y's, and then you're dividing by the width to get some sort of average. And it's the average. It's the equivalent actually of the area with the average over that region is the same as the original area under the curve, right? And this is the average value here. All right. So you can do the same thing for multivariable functions. The only difference is that you're doing a double integral to add up everything, and you're dividing by the area in the domain instead of the length in the domain. Okay, so all these ideas are extendable, and we'll look at many other applications of these multiple integrals as we learn how to compute them. Okay, so how do we compute them, right? We don't want to have to do this by adding up little heights and rectangle volumes, right? Like we could take some approximation here. If we made the number of rectangles larger, we would get a better approximation, and even better still here, right? But doing that, unless you're using a computer to numerically do that, takes forever, right? So we didn't actually compute integrals for definite integrals in this fashion in calculus, Calc 1B or AP Calc BC. Instead, we used the fundamental theorem of calculus, right, which said that if you had a function, you could find the antiderivative of that function and then take two copies of the antiderivative and plug in the b into the ending point into this and the starting point value of the integration variable into this one and subtract the two. And interestingly enough, although it wasn't intuitive, but it could be proved, that the value of the function curve is just set by the endpoints plugged into the antiderivative. So the curvature is taken into account by taking the antiderivative. So we need something like the fundamental theorem of calculus, except for multiple integrals, right? So how is that extended? Well, the idea is discovered by a guy named, I think it's Carlo Fubini, an Italian mathematician, and it wasn't discovered until 1907, interestingly. So they had to do things numerically or by division methods, presumably before this. But for most of the 1900s and the 2000s, we can use Fubini's theorem, right, which allows us to apply the fundamental theorem of calculus because it allows us to do what's called an integral, an iterative integration. So we can compute integrals iteratively. That means that we can think of this double integral as an inner integral. Okay, so we have an inner integral here. Let me identify that as inner. And then we can think of the outer integral as a second layer, right, the outer integral. And we can just ignore the outer integral completely and just do the inner integral first. And then when we get a result, typically it's an equation or a function, then we can then iteratively now do the outer integral on the result of the inner integral. And actually, it doesn't matter whether you put y first or x first as the interval. The only thing is you got to make sure that these things match. So if, for example, if you've written dx here, then that means that these limits of integration are x values. And dy here means that these are the y values, c and d, okay? And we can choose whichever way seems best. The best way to see this is just doing a bunch of examples. So I'm going to do some. We'll have a couple for you to do. and we'll start simple and move to more complicated scenarios. Okay. Let's say we had to evaluate this definite double integral, okay? The integral of this function x squared y, right, where y's are going from 1 to 2 and x's are going from 0 to 3, okay? So that means in the domain over here, right, we've got a region where the x's go from 0 to 3, but the y's go from 1 to 2. And so in 3D, this would be that domain region down here. And this function here, I'll mark it in green, this function here produces a surface, okay? The z is the output value, okay? So what we're basically doing is trying to find the area under the volume underneath this surface just in this region here, from here on down, right, over this part of the domain. Right, so we could pick whichever one. Let's do it in the order that it's written here. So what we could do is we could first do this part, okay? And I actually like to, well, I'll write it this way. Let me use two different colors here. So we have an outer integral here, 0 to 3, right? And we have an inner integral, which is 1 to 2 x squared y dy, right? And then the outer integral is the dx, okay? Sometimes I'll kind of keep writing it like this. There'll be other times, in fact, I'll work this one over again in another fashion, which I actually use more frequently. So the idea is we're just going to work on this blue integral first, okay? Now, while we work on the integral, it means that y is to be treated as the variable. And that means that while we're working on it, x is to be held constant. The idea behind that is that we're going to be looking at a particular slice, like a particular slice in x. So x will be treated as a constant, and then we'll integrate by moving across y, okay, to get like a volume, right, but just for one value of x. And then we will do that for across y. And then in a separate step, we will integrate across x. So let me just do the blue part first, okay? So we're treating the x as if it was a constant. It will be changing for different values of x, but while we're in the process of integrating y, x is held constant. So just like with partial derivatives, we just have the x tag along as a constant, but we do the integral with y. So this x here, I'm going to use the kind of fundamental theorem approach. The x squared is a constant, right? But in fact, I could even say that it doesn't participate in the antiderivative. We're taking the antiderivative of just this y. And the antiderivative of y using the power rule is 1/2 y squared. And then we have to evaluate that from 1 to 2. Okay, so so let's see, we've got, let's see, x squared there. And then by the fundamental theorem now, I can say that there are two copies of this, 1/2 something squared minus another copy, 1/2 something squared, right? Where I plug in 2 in the left version and 1 in the other version, right? So this number, the n goes here, and the start number goes here, right? So what does that evaluate to? That's 2 squared, which is 4 divided by 2 is 2, minus 1 squared, which is 1/2. So 2 minus 1/2 would be 3/2, right? So I've got x squared, that's considered a constant right now, times 3/2. That's the result of the blue integral using the fundamental theorem of calculus. So we didn't have to use rectangles. We could just do the antiderivative and plug in the way we normally would. So now I'm going to evaluate the outer integral. Okay, and so I would move the 3/2 to the outside since that's a constant and be taking the antiderivative of x squared, right, which will be 1/3 x cubed, right? And I have to plug in 0 and 3 there. So this is really the constant 1/2 when these 3's cancel. And I have to take my, let's see, I've got 3 cubed minus 0 cubed from the fundamental theorem of calculus. So we would have 3 cubed is 27 over 2. So we have 27 over 2, and that's the answer. So what that numerically means is that's how many cubic units of volume there are underneath this whole object, like from the surface down to the place in the domain down there, okay? So let me do that again, and I'll show you how I usually write this, just because I don't like copying this over and over and over again until I'm done. So this is what I would actually write, and I would recommend that you use this method. I would just pull out the inner integral first. I'll label this inner, or sometimes I'll put dy, and then I'll just evaluate that integral first. Okay, dy. While we're doing dy, right, this x squared is a constant, so it comes outside. I'm doing the integral of y. That gives me x squared. I have 1/2 y squared, 1 to 2, which gives me, by the fundamental theorem, 1/2 2 squared minus 1/2 1 squared, which ends up being 3/2 times x squared. So I just do that first without even bothering with the outside. And then I go ahead and write outer dx, and I do that separately. Now I go back and look at the original problem, and I insert my integral from here, pulling out the constants. So this would be 3/2, and then I'd have 1/3 x cubed, evaluated from 0 to 3. So that would be 3/2, 1/3 x, so 3 cubed, right? Minus 1/3 0 cubed. So I would have these 3's would cancel, and you would have 1/2 times 3 cubed, which turns out to be 27 over 2. So usually I explicitly do the inner and the outer separately. This is going to become even more important when we do triple integrals, because we'll have 3 integrals. And so we have 3 different things, and you don't want to have to keep writing things over and over and over again. Okay, so that's the basic idea. That's it. If you can consider this an integral, an inner integral, and then an outer integral. And by Fubini's theorem, we can do the inner integral first, take the result, and then multiply by the outer integral. Okay. Now, this particular example, we can even write a little simpler. There's a simplification method. It's a special case, and that is if you can take your integrand f of xy, and it can be written as 2 separate functions that are each a function of only one of the variables, like g just of x and h just of y, then you can actually evaluate the 2 integrals at the same time separately and then multiply the results. Let me show you what I mean by that. This x squared y can actually be considered 2 functions, x squared and y, that are multiplied together. And that means I can rewrite this as an integral for the x part, which would be, let's see, the x goes with the 0 to 3. So that would be 0 to 3 of just the x squared dx. And then a separate integral for the y part, y dy, from 1 to 2. And then we can just multiply those results. So if you can take your integrand and separate it into 2 factors that are multiplied, each containing only one of the variables, then you can do each of the letters, each of the variables integrals separately. In fact, this would turn out to be 1/3 x cubed evaluated from 0 to 3. This one would turn out to be 1/2 y squared evaluated from 1 to 2. So you would get 1/3 times 3 cubed minus 0 cubed, which is, let's see, 3 cubed is 27 divided by 3 is 9. And then this part over here would be 1/2. And then let's see, we would have 2 squared minus 1 squared, right? Which would be 4 minus 1 is 3, which is 3/2. And so that ends up being 27/2, which is even a little less writing and less work than the way we did it before. So you always want to be on the lookout for things that can be split. If you can split this, then you can do the integral separately, and especially later, that's going to turn out to be a real big time saver in some cases. Okay, but that is a special case, and we'll see examples with the special case and without. Okay, let's see another example. Let's say we wanted to do the double integral of dx dy of this function e to the x plus 3y, which at first appears to be, you can't split it, but actually this could be split, because e to the x plus 3y can be written as e to the x times e to the 3y, because using exponent rules, you would add these exponents back up to the common base. And that means you can separate this into one integral for the y's, right? So that would be 0 to 1 of the e to the 3y part dy, and a separate integral for the x's, 0 to 3 e to the x dx, right? So using the rules, right? The antiderivative of e to the 3x is the copy divided by the constant. evaluated from 0 to 1, and the antiderivative of e to the x is the copy, evaluated 0 to 3. Right? Use the fundamental theorem to plug in the end and start values, and this evaluates down to this expression here, which is a number because e isn't a variable, it's a constant. Right? Note, if you did not see that you could split this, you could still do this, but it would be much more difficult. The inner integral here, if you didn't see you could split it, you would have to do integration by substitution. Right? So we should be familiar with that. We will have to use that on some integrals. That's where you identify a composite function and you take the inside integral and give it a letter like u. Then you take the derivative of that to form kind of a toolkit to substitute back into the original integral. So if u is x plus 3y, du dx is 1, therefore du is dx. And that means you can take this inner integral, change the x plus 3y part to a u, replace dx with du, but then you have to replace the limits of integration. So if x is u, or sorry, x is 0, then if you plug that in here, u is 3y. So this has to become 3y. And then if x is 3 and you plug that in here, then u becomes 3 plus 3y. So when we do the antiderivative here, we get the copy e to the u, but then we have to plug in 3 plus 3y minus 3y here. And that becomes the result of the inner integral. So then we take that and now do the outer integral, where we're taking the antiderivative, treating y now as the variable. Okay, and so this can be separated into two separate terms, right? One is e to the 3 plus 3y dy. You can do each individual term, if we're adding or subtracting, as a separate antiderivative. This one over here is not bad, right? But this one's going to require substitution again, because you'd have to say u is 3 plus 3y, therefore dy du is 3, so du is 3 dy. And you could substitute back in here and solve, right? You'll end up, when you change limits of integration and everything, getting this, because you have to take, okay, so this 0 for u makes this 3 plus 3 times 0 is 3. And when you plug the 1 in, you get 3 plus 3 times 1 is 6. And then there's a constant 1/3, because replacing dy would therefore equal 1/3 du, right? So all of our Calc 1 type integration stuff, right? We need that. But now you've got something where each of these can be done with a simple antiderivative and then applying the fundamental theorem, and you'll get the same answer, right? But the point is that's a whole lot more work than if you note that this is actually a special case. You can separate this into two factors that each contain only one of the variables. And this gives a preview for what's going to happen when we can't do that, right? You're going to have to somehow sometimes you will get antiderivatives here, which are complicated functions of the outer variable as the result of the inner integration. All right, let's keep looking at examples here. Here's another one. Here's one where we can't separate, right? We have an integrand that's 4x cubed minus 9x cubed y squared, and there's no way to factor anything out here, right? You can factor an x squared out of the whole thing, but that still leaves it. I mean, you could factor an x squared out, let me write that, but you would still have 4x minus 9y squared. So this factor here still contains both variables. So there's no way that you can factor this for the special case. So in that case, you do kind of what we did in the last screen. You just go ahead and work with the inner integral, but you remember to treat the other variable as a constant. So while we're doing the inner integral here, which is dy, we treat the x as if it was a constant. So for this term, the antiderivative would just be, this is all one big constant. So this would just be the constant times y is the antiderivative. And then here, this 9x squared part is a constant, right? But when you do the antiderivative of y squared, you get 1/3 y cubed. So let me just show that over here. If you were to you have the 9x squared and you're doing the antiderivative of that, you would get 9x squared, and this would be 1/3 y cubed, and that's why I have 9 times 1/3, drop this constant to a 3. We still have the x squared, but now we have y cubed. And then you would be plugging the limits of integration 1 and 2 in here, actually evaluating when you plug in start and end to get this expression. That's the result of the inner integral. Then you take the outer integral of that result, right? And so now treating x as the variable, right? This would be the antiderivative here is x to the 4th. The antiderivative here is 7x cubed. and you plug in 1 and 0 to finally get -6 as the result. So it's not impossible if you can't do the special case. It's just more work is all. Okay? And sometimes you can do the special case where you factor and separate, and sometimes you can't. All right. So I've got a couple here for you to try. I would like you to pause the video and try both of these. This one on the left you can separate, and the one on the right you can't. So pause the video, give these a try, and then unpause. Okay, so for this one, I can separate this into x times sine of y. So what I'm going to do is say, okay, the y values here are these inner values, and the x values are the outer values. So let's do the x's. The x's are going to be integral from 0 to 2 of just the x factor, and then this will be 0 to pi over 2 of the y factor. So the antiderivative of x is 1/2 x squared, evaluated from 0 to 2. The antiderivative of sine is cosine, negative cosine actually, right? Because the derivative of sine is cosine. The antiderivative or the derivative of cosine is negative sine. So is that right? Sine is cosine. Yeah, right. The antiderivative is negative cosine. I just have to think about that. So then plugging in here, we would have a half, and this would be 2 squared minus 0 squared. Over here, we're going to, so that evaluates to 4 divided by 2 is 2, right? And then over here, we would have negative cosine of pi over 2 minus negative cosine of 0. And on a unit circle, pi over 2 is up here, 0, 1. The cosine is the 0. So pi over 2, the cosine is 0, so this is just 0. Minus negative, so plus cosine of 0. Over here at 0, cosine is 1. So this would be 1. So this will be 2 times 1 or 2. This evaluates to 2. So if you got 2 there, that was correct. Okay, now this one we can't separate. So I can't really factor that in such a way that the x and y's end up in separate factors. So we're going to do the inner dy integral first. So that's integral from 1 to 2 of, okay, now since I'm treating the y as the variable, I'm going to write this as the constant x times 1 over y plus 1 over x as a constant times y dy. Okay, so the antiderivative of 1 over y is the natural log, right? And the x is a constant. So this is going to be x, and then the constant, that's a constant, natural log of the absolute value of y. Now for this term, we have 1 over x. The antiderivative here will be 1/2 y squared. And then we're plugging 1 and 2 in for the y's. So that would give me, let's see, x times natural log of 2 minus x times, well, really, I can keep the x on the outside. It's a constant. Natural log of 2 minus natural log of 1, right? But natural log of 1 is 0. And then I've got, let's see, a constant 1 over x, 1/2 2 squared minus 1/2 1 squared. So 2 squared is 4 divided by 2 is 2 minus 1/2, which would be 3/2. So it looks like I've got x natural log 2 plus 1 over x times 3/2. Is that right? Yes, okay. And then the outer integral, give me some space here. The outer integral, I guess I need to write it first. The outer, which is dx, is going to be the integral from 1 to 4 of this result. So x natural log of 2 plus 3/2 1 over x, evaluated where x is considered the variable. All right, so let's see, antiderivative here. So the natural log of 2 is a constant. This will be 1/2 x squared. And then I've got the 3/2 constant. The antiderivative of 1 over x is natural log of the absolute value again, evaluated from 1 to 4. And I will ask you, when they're fairly simple like this, to do these integrals by hand, right? We need to do some practice. At a certain point, I'll have you switch to using the calculator, but like Math 9. But for now, I'd like you to do these by hand. So we've got the constant natural log of 2 and 1/2. And then I've got x squared. So I've got 4 squared minus 1 squared. I've got 3/2 times natural log of 4 minus natural log of 1, which natural log of 1 is 0. right? So it looks like we've got 4 squared is 16 minus 1 is 15, so it's 15 natural log of 2 over 2, right? Plus 3 halves natural log of 4, right? And actually, there's things we could do here, like if you really wanted to be fancy, like if you're trying to match the answer in the book, they're probably going to have this, they're going to do some work here. They're going to go, this is the same as natural log of 2 squared, which means it's 2 natural log of 2, which means if you multiply that by 3 halves, this is 3 natural log of 2. Then you've got 15 over 2 natural log of 2. And since they're both the same natural log of 2, you could end up taking 15 halves plus 3, which would be 15 plus 6 over 2. And that's why we're going to get 21 over 2 natural log of 2. That's probably going to be the answer in the book. Okay. Okay, questions on that? Hopefully you were able to do that example. So I just want to go through a few other examples here, actually 3 other examples that are pretty complicated, just to show you the kinds of things that can come up. Okay, so the next one, let's say we had this, and we're doing the integral of xy squared over x squared plus y over some area, and then they just say over region R, and then they tell you the region, right? So that means you have to figure out what you want to do here, right? And you could pick either one, y or r, whichever one you feel is easier to do, right? In this case, I don't think it matters, because I actually can split this up into 2 factors, right? This part right here has only x, and it's multiplied by y squared. So I can do one integral for the x part and another integral for the y part. And so the x part is just going to be from 0 to 1. The y part's going to be from -3 to 3. On Thursday, when we move on to 15.3, we're going to talk about regions that are not rectangles in the domain. And in that case, these integrals, the inner integral will involve functions instead of constants. But for now, we're going to keep things simple and deal with this with constants. The integral on the right here is not too bad. It's just 1/3 y cubed, and then plug these numbers in, and you get 18. On this one is a little more involved, right? We're going to have to do either substitution or integration by parts, but actually substitution works here, because if you treat the entire bottom of the fraction as a function you call u, and do a u sub on x squared plus 1, then du would be 2x dx. Then that means, let me actually show this step over here. You have 1 over x squared plus 1 x dx from 0 to 1, right? And now we're just saying that this is u. And if I've got du is x dx, then I can substitute out the x dx part here, because that's just equal to 1/2 du. So I'm going to have 1/2 du in there, right? And then I would want to change the limits of integration here, right? So if x is 0, then plugging this in here, that makes u 1. And if x is 1, that makes u 2. So that's where I got this 1 over u, 1/2 du from 1 to 2. And then we're really taking the integral of 1 over u, which is natural log, plugging in and getting 9 natural log of 2, and then times the 18 from the other factor, right? When we're all done, actually this becomes this. So this is 1/2 natural log of 2 minus 1/2 natural log of 1, but log of 1 is 0. And so when you multiply all this together, this 1/2 times the 18 gives you the final answer, 9 natural log 2. Okay, so point of that one was, if you're not given the region, right, or the limits, but you're given the region, then you have to somehow figure out from the information in the problem what the limits of integration are. And you're free to put this in whichever order seems best. It doesn't really matter if we're going to split. Sometimes it does matter, though. Okay, let's do another example. Integral from 0 to 2, 0 to pi of r sine squared of theta, d theta dr. Okay, so we have 2 variables here, r and theta. This is actually something to come up later when we talk about polar coordinates. We'll talk about that more fully later. But right now, if they go ahead and give you this with limits of integration, you can just treat the r and the theta as variables the same as if they were x's and y's. Right? Later we'll talk about the geometric meaning of this and how that helps in certain kinds of regions. Okay, but for now, I notice that I can separate r and sine squared of theta, so I can do those 2 integrals separately. Right? The r one is really straightforward. It's 1/2 r squared evaluated from 0 to 2, which turns out to be 2. right? This one is quite a bit more involved, sine squared. So there's a couple ways we could go about doing that. One way, which you're allowed to do on our test, is we're going to allow you to use the table of integrals in the back of your textbook, and I will make copies of that and make it available so that you can do this. Okay, but the tables are developed mainly from using identities, especially for trig functions. So sine squared, there's a trig identity that says that that's 1 minus cosine of 2 theta over 2. And so if you replace that and then pull the 1/2 out, you have two terms here, the integral of 1 and then the integral of cosine 2u. And if you do a u sub for 2 theta over here, you add, where you say this is 2 theta, then this would be the integral of cosine of u. And then the d theta part would be written as 1/2 du. So I would have a 1/2 to join this 1/2, and actually this is a typo in the notes. This should be a du here. Okay, so a typo in the notes there. Let me correct that over here as well. Du. Okay, and so then we end up getting the antiderivative of cosine is negative sine, and then we would plug in the 2 pi and the 0, but it ends up being 0 minus 0 anyway. So this whole thing is just 0. So for this term of it. But we still have this term, which is just theta, the integral of 1. So let me write that more explicitly. We have 1/2 times the integral from 0 to pi of 1 d theta. And the antiderivative of 1 is just the variable, which would be theta. So then by the fundamental theorem, you would say plug in pi, 0, and we have pi times 1/2. So even though this part of it is 0, we still have 1/2 pi here. We have the 2 from this part, and so the final answer here is pi. So the point of this example is that you don't have to have x's and y's. As long as they give you this and don't make you figure out the region, you can treat those as generic variables. Sometimes trig identities are needed, or you can use integral tables to evaluate. Okay, and then this is the last example. Let's say we have the function x sine of x plus y evaluated over an area, two-dimensional area called R, and x is going to go from 0 to pi over 6, and y goes from 0 to pi over 3. Okay, so let's start by just making this x and y. It probably doesn't really matter here which one we go first in this case, because we're talking about rectangles. Later on Thursday, it will definitely matter which one we do first, dx or dy, because in some cases the integral will be much easier to evaluate. Now, unfortunately here, we are not able to factor this in some way, right? I can't really write this in some way where the x's are completely separated from the y's. So I'm going to have to do just the inner integral first here, which is this is an integral from 0 to pi over 6 of x sine of x plus y. Very complicated structure. We can't evaluate it directly with any shortcuts. There's no u substitution that works. Okay. Remember, we're treating y as if it's a constant. So even if you thought of this as x sine of x plus 2, right, there's still no direct u substitution that will work, right? Because if you make u the x plus 2, then the derivative is 1, and there's this extra x left over, right? So in this case, we want to use our old friend integration by parts. So I wanted to include one that involved that, just to remind you to do how integration by parts works. So integration by parts is when you have an integral that you can write integral of u dv, and by the product rule done backwards and then antiderivative, you can show that that's equal to uv minus the integral of v du. Most of us just memorize this structure, right? Then the idea is that you have to split this up into a u and a dv. And the idea is you want to pick a u where when you take the derivative to form your toolkit of stuff here to substitute into here, that you get simpler structures, right? And the dv, when we take an antiderivative to turn that back into v to get this v, we want that to not get more complicated if possible. So the right selection here would be to pick x as the u, this is u, and then all of the rest of this is dv. The differential always has to end up in the dv. So what I always had my students do in brief calc is just to write the u, write the dv out, and then remember that you take the derivative here to complete the toolkit to get the du to substitute in, and you take the antiderivative to get the v to substitute in here and here. So if we have u as x, then du dx is 1, so du is dx. That gives me the u and the du to substitute here and here. And then if dv is sine x plus y dx, then you just take the antiderivative of both sides of that structure. The antiderivative of 1 is the variable v, and the antiderivative of sine is the negative cosine. And because this is x plus a constant, if you had done u substitution, the du would just be dx anyway with the same limits. So this is just treated as a constant, and therefore this is just negative cosine of x plus y. If you don't believe that, you can do that. Let me just do this one time and show you that you could do that. If you made a u substitution for x plus y, du dx would just be 1 because this is a constant right now. So du is just dx. And then you could rewrite this as the sine of u, okay? And then this would just be du. And since du and dx are the same, right, this is just a constant, you're going to get the same integration limits, right? Actually, we don't even have the integration limits on here at this point. So you're just taking the integral here, which is negative cosine of u. And so that would just be the negative cosine of x plus y again, right? In other words, there's no fraction that has to get pulled out here. So because this doesn't participate in the derivative part. So it's fine to just write this as negative cosine of x plus y without having to show this u substitution. Okay, so now I have my, let me do this again. I have my let's see, let me highlight over. I have u, I have du, and I have v. And these things get substituted into the integration by parts expression. So the u is x, that's this, right? In fact, let me do it over here. The u is x, the v is negative cosine x plus y, minus the integral of v, which is negative cosine x plus y, and then the du, which is dx, okay? So that's what I've got written here, negative x cosine x plus y minus a negative, so that's going to become a positive cosine. And then the antiderivative of cosine is going to again be a sine, right? And then finally we're at the point where we can plug in the pi over 2 and the 0 in for the x's, the x, okay? So at this point we have, let's see, we have our negative x cosine x plus y plus the antiderivative of cosine is just straight sine. And now I'm going to plug these two x values in for the x's, okay? So I've got negative pi over 6 cosine of pi over 6 plus y plus, let's see, why is that a 0? Oh yeah, plus, so minus, I should have probably been more explicit, minus this expression with 0 plugged in. Maybe I should actually show that up here. So I've got negative the x value, and then the cosine of pi over 6 plus y, just being treated as a constant, minus that whole expression, negative, but this time with 0 plugged in, 0 cosine of 0 plus y, right? And so this whole part here becomes a 0, right? This part just goes away because it's a 0. And then plus this term with this plugged in first and then 0 plugged in first. So we end up getting this whole expression here, right? This term dropped out because of the 0 being plugged in for this x. And then we have to take now the outer derivative, which is the integral from 0 to pi over 3, now treating the y as a constant, or as the variable. And there are 3 terms here, right? Each of them can be done just with a straight shortcut because they're the variable by itself without any multiplier inside there. So this antiderivative of sine is cosine, this antiderivative of sine is negative cosine, and this antiderivative of sine is negative cosine. So this changes sign. And then we take that expression, plug in pi over 3 for all the y's, subtract the expression over again with 0 plugged in. That is a lot of writing, right? But in the end, if you carefully plug everything in, you get square root of 3 minus 1 over 2 minus pi over 12. That's the answer. So this can be pretty intense, obviously, depending on how complicated these are, right? A problem can either be really hard or quite simple. But the procedure stays the same. You either can separate them and do them separately, or you have to do the integral of the inner part first and take the resulting expression, take the outer integral of that. All right, that'll wrap up the 15.1, 15.2 lesson.